comunicación con esta charla que nos va a impartir el profesor Ozeri. Pero antes de darle la palabra a él, me gustaría agradecer particularmente al doctor Daniel Smith por facilitar y ayudarnos en la gestión para que esta conferencia se pudiera llevar a cabo el día de hoy. Muchísimas gracias. También permítanme presentar al doctor Ozeri de Weizmann Institute of Science, quien es nuestro invitado de honor en esta tarde. También contamos con la presencia del doctor Fernando Ramírez Martínez, quien es nuestro secretario académico de nuestro instituto y quien a nombre de la doctora Pilar Carlos Castro nos dirigirá algunas palabras a nuestros invitados.
Welcome, Professor Roee. We're very, very pleased to have you here. Your research gets us very, very close to our interest. So we are very, very interested in hearing what you have to say, and particularly about quantum computation and your work there. So I would like to, in the name of the director of the Institute, give you our welcome. And I hope that this is the first time of many visits to our institute. Thank you very much.
Asimismo, pues es la oportunidad para poder entablar una serie de colaboraciones, de vínculos, de alianzas con el Instituto Weizmann. Y en ese contexto, pues la presencia del doctor Smith como CEO de la oficina de este instituto en Latinoamérica, pues puede abrirnos grandes oportunidades, pues no solo para que nuestros investigadores puedan establecer vínculos de colaboración con este instituto, sino también para nuestros estudiantes de licenciatura, estudiantes que están iniciando su posgrado, que eventualmente pudieran realizar en algún momento alguna estancia de investigación en este importante instituto. Entonces, pues, bienvenidos todos. Y antes de darle la palabra al doctor Ozeri, permítanme platicarles un poco de su trayectoria académica. El doctor Ozeri nació en Israel, tuvo el grado en física de la Universidad Hebrea de Jerusalén, recibió sus títulos de maestría y doctorado en física en el Instituto Weizmann en Ciencias, realizó una investigación postdoctoral en el Instituto Nacional de Estándares y Tecnología de Denver en Colorado, Estados Unidos, en el grupo del doctor David Weizmann, ganador del Premio Nobel de Física en 2012. Se incorporó al cuerpo de docente del Instituto Weizmann en 2007 y fue nombrado vicepresidente de Desarrollo y Comunicación en diciembre de 2019. El profesor Ozeri recibió el premio Rosa y Emilio Segre en investigación en 2019, también el premio Morris Levinson en física en 2012 y la prestigiosa beca postdoctoral del Fondo Rothschild en 2003. Sus artículos se han difundido en reconocidas publicaciones científicas especializadas en física como Natural Science, Physical Review Letters, entre otras. El profesor Ozeri realiza investigación en el campo de los átomos fríos. Una de las áreas de investigación también es la computación cuántica, en uno de los mayores desafíos científicos por encontrar formas de mitigar el efecto del ruido de los sistemas cuánticos. Y pues como ustedes saben, algunos de nuestros investigadores pues trabajan cerca de esta investigación y pues de ahí este interés puedan encontrar vínculos que tiene desarrollar. Pues bienvenidos todos. Welcome, Professor Ozeri, for being here. So, you want to start?
Sí, es un gusto estar aquí. Conocemos UNAM, sabemos del tamaño, la calidad y el impacto, no solo en México, sino en el mundo. En el Instituto Weizmann tenemos la suerte de contar con estudiantes del Instituto de UNAM estudiantes avanzados. Y esta es primero agradecer la posibilidad de estar aquí, pero también una invitación a crear un vínculo más fuerte, en este caso en los temas que van a ser hablados hoy, pero puede ser en cualquier campo de la ciencia, de la ciencia, en ciencias exactas y naturales. Esos son los campos del Instituto Weizmann. Quiero decirles que cuando me enteré que esta conferencia iba a ser aquí, en el Auditorio Moshinsky, me emocioné muchísimo porque sé que Marcos Moshinsky fue una persona muy importante aquí en México, pero también una persona importante para nosotros. Tenía una relación importante con el Instituto Weizmann. Y en el 2004 ganó un premio muy importante del Instituto. Entonces nos sentimos en casa, nos sentimos en casa por estar en el UNAM y nos sentimos en casa por estar en el Auditorio Moshinsky. Después, con mucho gusto, puedo compartir con ustedes mis datos y podemos intentar crear un vínculo académico de colaboraciones científicas y de poder recibir estudiantes de la mejor manera. Gracias por recibirnos. Profesor Roee, Ozeri, please.
Thank you all very much for having me here. It's a pleasure and honor speaking here. What I'd like to tell you about today is about quantum computers. Now, I understand this corresponding that the audience here is a bit mixed. So some people are experts and some people are not as experts. So I'm trying to build a presentation that on one hand explains some of the basic principles of quantum mechanics and quantum computing, and on the other hand, continues to some more technical aspects. But if you feel that I explain things that are obvious, please let me know. And if I speak about things that you don't understand, then let me know as well. And you're always welcome to ask questions in the middle of the talk. So this can turn into a conversation if you like. Okay, so I call this talk "Quantum Computers Taming Schrödinger's Cat." Quantum mechanics is the physics of the microscopic world. It's physics that governs the behavior of electrons and atoms. It's not the physics that governs the behavior of cats. Schrödinger was the first to use the Schrödinger cat, the Gedanken experiment, as a way to contrast the microscopic with the macroscopic world. Building a quantum computer, in many ways, is trying to take quantum mechanics and engineer its way into quantum microscopic skills. So in that sense, we're trying we're trying to create a macroscopic system that would nevertheless obey the laws of quantum physics. What we do in the lab is actually develop and build these quantum computers. What you see here at the top is an image of 8 trapped ions. In this case, these are strontium plus ions. The exact species doesn't really matter. The reason that they're arranged in this crystal is the following: they're charged, they repel each other. We cool them using laser cooling techniques, and I know that you have laser cooling labs here at UNAM as well. We cool them using laser cooling techniques to temperatures that can be as low as 900 Kelvin if we need to. So their kinetic energy is very, very low. On the other hand, they're trapped, and they're trapped by electric fields that we apply using a set of electrodes. In this case, it's a set of electrodes that we fabricate on a chip. So on the one hand, the set of electric fields confines the atoms, and due to their repulsion, they arrange along the subdimension of the trap. And we use each one of these atoms as a quantum bit. So if you like, this is a quantum byte based on trapped ion qubits. So to explain kind of the basic principles behind quantum bits or quantum mechanics, I think it's instructive to start thinking of a simple system, relatively simple system, which is an interferometer. An interferometer is a device that takes a wave, splits it, and then combines it in a way that the two paths interfere. Okay, so we can think of a laser beam that enters an optical path, hits a semi-transparent mirror. Some of the laser light is going through, some of the laser light is being reflected, and then using two mirrors to recombine these two paths, you get on another semi-transparent mirror, and light can exit either through port A or through port B. So again, light can go to path 0, can go to path 1, and then exit the interferometer on exit A or exit B. Now let's think about the situation where the light is built sufficiently such that there's only a single photon entering the interferometer. Now in this case, we can ask whether the photon moved through path 0 or path 1, clearly, right? And we can ask whether the photon exited on exit A or exit B. Well, the interference of the two paths of the photon will determine whether it exited on A or exited in B. The phase difference between these, the wave function of the photon going through these two paths will determine whether it exited to port A or port B or both. So the superposition principle tells us that quantum systems do not necessarily have to be in a single physical state. They can be in a superposition of physical states. And we assign a number, which is the amplitude in which they exist in these two physical states. And the amplitude carries two pieces of information. One piece of information is the probability that it will measure these two, this quantum system in state 0 or state 1. And the absolute value square of alpha and beta gives us these probabilities. And the phase difference between alpha and beta are complex numbers, gives us the phase information between these two paths. So when we interfere these two options, that phase difference determines, if you like, the photon would exit at port A or at port B. Now, because alpha and beta are complex numbers, that means they have 2 free parameters in them. And because the global phase of that thing doesn't matter, so we don't care about the phase of one of them, we only care about the phase difference between them. And because alpha squared and beta squared are probabilities, that means that the sum of these two numbers should equal 1. We have 3 numbers, and the sum of these 3 numbers squared should equal 1. That means that geometrically, we can present this as a vector pointing a sphere that has a radius that equals 1. So a geometric way of presenting the state of a quantum bit as we can represent it geometrically as the vector that points on the surface of a sphere that has a radius 1. We call this sphere the Bloch sphere. So we've described the physical state of a quantum two-level system. But what about if you want to measure this superposition? So let's say, if we don't measure this superposition, the photon can go through path 0 or path 1. But what happens if we insist on measuring in which of the paths the photon actually traversed? If we place photodetectors in the path of this photon, then we're going to measure the photon either in state 1 or in state 0. We're not going to get interference at all. So quantum measurement actually projects the state of that quantum two-level system on one of these two possibilities, either 0 or 1. So, this was a very quick explanation of the superposition principle. How is quantum mechanics and quantum superpositions, how are these systems related at all to computers? First person to conjecture that there is a connection between quantum systems and computers was Richard Feynman in the mid-1980s. Richard Feynman, back in those days, tried to investigate the limits that physics imposes on computation. What is the minimal energy that a computation needs? Are there limits to the entropy which is generated, or is entropy generated during the computation? He wanted to understand whether physics imposes limits on our ability to compute. And during these investigations, he came to the conjecture that using quantum computers, we will be able to perform computations that we can't perform today. And to put it in relatively simple terms, the logic that guided Richard Feynman was the following logic. So if we encode information in bits, it's digital information. We encode information in two-level system. That switch can be in either 0 or 1. That's how we encode information. A qubit, a quantum bit, as we just learned, can be in a superposition of 0 and 1. What happens if we have 2 bits, 2 such switches? Then 2 such switches can be in one out of 4 different possibilities: 0, 0, 0, 1, 1, 0, and 1, 1. 2 quantum bits can be in a superposition of all these options. Okay, each one with its own algorithm. 3 switches like that, 8 different options. 3 quantum bits can be in a superposition of all 8 possibilities with the corresponding algorithms. Okay. The rule is 2 to the power of the number of bits that you have. Okay. 2 options for each of the bits. And what happens if you have 100 bits? When you have 100 bits, the number of possibilities is 2 to the 100. 2 to the 100 is, roughly speaking, a third of the number of atoms in the whole universe. Okay. If you would need to store 2 to the 100 different options in the memory of your computer, even all the atoms in the universe would not be sufficient to store that information. This number is ridiculously large. A quantum computer, though, in principle, could be in a superposition of all these 2 to the 100 possibilities. So one way to think of a quantum computer is the following. You remember that when you have superpositions with different states, and there is a phase relation between these different states, we can interfere between these different states and have them exit at different ports according to the phase difference between them. One way of thinking of a quantum computer is, again, as an interferometer, as a wave machine that hosts many paths. Okay? But in this case, if you have 100 qubits, this interferometer has 2 to the 100 different paths. This is a ridiculously large number of paths. Nevertheless, if we can control the phase difference between all these paths, eventually we can make it so that the output from this interferometer would go in one of the 2 to the 100 possible outputs of this machine. And this output is the answer to your computation. Okay. So one way of thinking of a quantum computer is as a quantum system. It's a computer. It needs to have an input and an output. The output would be the solution to the computation which the input imposes. And it's a wave machine. It's a wave machine with an exponential number of interfering paths, and all these paths need to interfere such that the output of this machine would be the answer to your computation. Now, this is a fairly complicated system. Okay? Anybody who worked with an optical interferometer learned on their own flesh, agony and the pain of being able to maintain 2 interfering paths stable and make sure that light comes out of the interferometer without any noise. A quantum computer is a pretty fancy interferometer that needs to maintain the stability between 2 to the 100, or 200 in the case of 100 qubits, but an exponentially large number of interfering paths. How are we able to generate this particular interference pattern between this large number of interfering paths? So you know that when we describe quantum states mathematically, we describe them as very long vector, and each entry in the vector is the amplitude in whatever state the quantum system is. And the computation looks like a matrix that acts on this vector. It's a pretty large mathematical operation. The mathematical operation is so large that it has an exponentially large number of parameters that we have to determine. So how do you do that in the lab? How can you generate an operation which has an exponentially large number of parameters that we control? That's pretty much impractical. And the people who initially thought of quantum computing took their inspiration from regular computing. In regular computing, we have a register of an X number of bits. And we want to implement a Boolean function on this input register. Okay? We have an input register of zeros and ones, and we want to operate with a function that acts on these zeros and ones. Now, how do we do that? That function can have many parameters. And the way we do it in classical computing is by breaking that Boolean function into much smaller, simpler operations. But we need to break it into a set of simple operations that are universal, in the sense that any function we would like to implement can be broken into a particular series of these simple operations. So here's an example for a set of universal gate set in regular computing. So if your computer has the operation to flip the state of each bit, I'm sorry, take the state of each bit from 0 to 1 or from 1 to 0. And it can perform a control dot. Control dot is a flip of a bit, of a target bit, which is conditioned on the state of a control bit. So the truth table looks like this. If the control bit, which is the first bit, is at 0, the state of the target bit is not flip. So 0, 0 goes to 0, 0, 0, 1 goes to 0, 1. If the state of the control bit is 1, the state of the target bit flips. So 0, 1 goes to 1, 1, 1, 1 goes to 1, 0. If you have both these operations on any bit in your register and on any pairs of bits, pair of bits in your register, you will be able to carry out any Boolean function. That means you can carry out any computation you like. Similarly, in quantum computing, there are sets of universal gates, in the sense that if you have these gates on any qubit and on any pair of qubits, you will be able to perform any quantum computing you like. You will be able to carry out any quantum operation, that huge matrix that acts on a vector of amplitudes, in your quantum computer. There are several examples for universal gate set in quantum computing, but here is one option, and that's probably the most popular option of the textbooks. One operation is the analog of the classical knot. And that is a rotation. Remember that a qubit is represented by a vector on a unit sphere. So this would be a rotation of that vector anywhere on the sphere. Okay. If I rotate that vector from the 1 state to the 0 state, that's exactly the knot operation classically. But in quantum mechanics, I don't have to flip the vector by 180 degrees. I can rotate it to anywhere I'd like on the block sphere, and that rotation is described to two rotation angles. The second gate in that set is the gate which is analogous to the classical control knot. In this case, the state of a target quantum bit would be rotated by 180 degrees, conditioned on the state of the control bit. Now, unlike classical computation, this operation can actually lead to pretty peculiar quantum states. Let's look at a simple example. If I have a quantum system which has 2 quantum bits, each one of these quantum bits is in a different superposition. So the first bit is the control bit, the second bit is the target bit, and let's assume that the target bit is in the 0 state. The control bit is in a superposition of 0 and 1. What happens if I now act with a control NOT gate? If I act with a control NOT gate, I'm going to rotate the state of the target bit only in the part of the superposition where the control bit is at 1. So if I do that, I will get a quantum system which is in either the 0-0 state or the 1-1 state. Okay. Now, why is this state interesting? This state is interesting because the 2 quantum bits are correlated, but they're correlated in a way in which I can't know a priori in which of the states they are. I know that I'm going to find them in the same state. I don't know in which state they're going to be. And in fact, I can take these 2 quantum bits and separate them by huge distances. If I measure one of them, the other one is going to immediately collapse to the result of the measurement of the first. And that's going to happen instantaneously. Actually, this phenomenon, which is called quantum entanglement, bothered physicists very much. In fact, the most famous argument against this faster than light action, if you like, was put forward by Einstein, Podolsky, and Rosen in the 1930s. Einstein, Podolsky, and Rosen viewed this as an argument against quantum mechanics and suggesting that there is a local hidden variable theory that underlies quantum mechanics. Today we know that they're wrong. There is no local hidden variable theory. In fact, the Nobel Prize in Physics this year went to the three pioneers who, through experiments, were able to prove Einstein, Podolsky, and Rosenbaum were able to prove that quantum entanglement is actually a real phenomenon. So you can see the Nobel Prize quote here, which says, for experiments with entangled photons, establishing a violation of Bell inequalities and pioneering quantum information science. So quantum entanglement is a funky phenomenon in nature, but quantum computing suggests that it's not just a funky phenomenon in nature, it's actually useful. So quantum computers actually use this entanglement phenomena constantly for their action. So what are quantum computers good for? I think that it's not as if quantum computers are machines that would solve any problem more efficiently than regular classical computers. Today we're familiar with roughly 3 families of algorithms in which quantum computers, we believe, would outperform regular computers. I listed here a list of 5 different examples, but there are many more. And I think that today there are dozens of quantum algorithms. As I said, all of them fall roughly under 3 families. So one famous example is the Shor's algorithm for factoring. That's an algorithm that will take a very large number and break it to the product of the prime constituents that compose it. This is the mathematical operation which is behind public key cryptography, which means that for classical computers, because that operation is exponentially difficult, it is impossible for us to break codes that are based on this RSA method. Quantum computers will be able to polynomially relatively easily calculate this task and therefore break contemporary public key cryptography. This is also the reason why governments view quantum computing as a strategic technology. Unstructured search, so random search within large databases, Grover's algorithm, finding a specific input by an Oracle query. This is a task which is exponentially difficult for a classical computer. It's also exponentially difficult for a classical computer, but it's exponentially difficult with an exponent which is half. So that means we still can't do it for extremely large numbers, but we can do it for numbers that are twice as large. And I've listed here pattern matching, quantum simulation. I think one of the ideas that led Feynman to think that quantum computers are better than regular computers was the fact that quantum systems are too difficult to simulate for classical computers, whereas quantum systems are naturally fit to simulate quantum systems. So quantum simulation is certainly one of the tasks that quantum computers work on. In the last decade or so, people have put forward computations which are not quantum and not classical, but rather hybrid quantum computations. These computations are actually heuristic in their nature. So at least as of today, we can't say anything about their computational strength. We don't know if we'll gain anything by working these algorithms, but people tend to believe that we will benefit, and actually people use them already. There are, as I said, there are many more examples. In terms of complexity theory, where do quantum computers reside? So for those of you who are familiar with complexity hierarchy, there are problems, P problems. These are problems that are polynomially solvable. The NP class is a set of problems in which the solution to the problem can be verified in polynomial time. So P, the set of problems that can be solved in polynomial time, clearly resides within NP. The question whether P equals NP is an open question in computer science. And one of the biggest open question in computer science. What people tend to believe today is that PQP, which is the complexity class of quantum computing, it's called bound error quantum polynomial, is larger than P and reaches within NP. Okay, so there are problems that today we can't solve in polynomial time, but having quantum computers, we will be able to solve in polynomial time. The promise put forward by quantum computers is of course a big incentive, big motivation, both for governments who would like to push quantum computing as a research discipline in different countries in order to make sure that that technology exists. So if we look at the current map of investments by governments in quantum computing, and these are programs that are currently at work. Most of these programs are 3 years in length. The total global investment is roughly around $30 billion, with China responsible for about half that expenditure. So global investments are rather large. And I would guess that these are the public numbers. I would guess that there are big numbers. I can't tell whether larger or smaller, which are classified. It's not just governments, the private sector is also investing very heavily in quantum computing. All the large technology companies like Google, like IBM, like Intel, like Amazon and Microsoft, all of them have quantum computing R&D effort in-house. On top of the big companies, there are probably about 50 or 60 startups worldwide, which are working towards developing and commercializing quantum computing technology. Some of these companies already offer quantum computing services on their machine through cloud services. So both Amazon AWS, Microsoft Azure, IBM Quantum, all of the services you can log in to cloud services, connect to a quantum computer and run your quantum code. So quantum computers, when I entered this field 20 years ago or so, this was to a large extent the promise. I think that today we see that promise, slowly being fulfilled. I want to say a few words about quantum computers and their sensitivity to noise. As I said, one way of thinking of quantum computers is a very large interferometer with an exponential number of paths that need to interfere for the computation to succeed. That means that we need to maintain phase stability over an exponential number of paths. And moreover, we can measure the state of our quantum system as the computation advances to the interferometer. And actually, these two concepts are very related to each other. And that means that quantum computers are also exponentially sensitive to noise. If you think of each of these paths as a path which is sensitive to noise, the more qubits you add to your system, the number of paths increases exponentially. And therefore, the sensitivity of your interferometer to noise grows exponentially as well. This is kind of when you think of Schrödinger's cat, right? The stark contrast between the microscopic world and the macroscopic world. Why don't we see quantum superpositions at the macroscopic scale? This is, as far as we know, really the answer. It's because large quantum systems are exponentially more sensitive to noise, and that's why the interference effect, which is the hallmark of quantum mechanics, disappears when we go to large systems. So in that sense, developing quantum computers is really the attempt to engineer a Schrödinger cat. Okay, we're trying to build a system with an exponential number of interfering paths that is still stable, but the sensitivity to noise is huge. And the noise is probably the biggest enemy of quantum computers today. I'll just say that even in the presence of noise, there have been at least 4 demonstrations so far, all of them in the last 4 years, I believe, in which quantum advantage has been demonstrated, in which a quantum computer carried out a computation that classical computers would not be able to calculate in reasonable time. Two such examples are a demonstration by Google, I believe from 2019, using a superconducting qubit quantum computer and 53 quantum bits, and even in the presence of noise, a certain problem that was used in this particular computation. These are problems that come from a set of problems called sampling problems. Google's quantum computer was able to solve that algorithm in a time which is significantly shorter than any classical computer would be able to solve. Another example came from China, the National Laboratory of Hefei, using 100 photons. In this case, photons were used as quantum bits. And in both these experiments, despite the fact that we have noise, and we call these quantum computers noisy intermediate scale quantum computers, the reason we call them noisy is because they suffer from noise. The reason we call them intermediate scale is because you can't really go to extremely large quantum computers. As I said, your sensitivity to noise grows exponentially. Nevertheless, they've been able to show quantum advantage and prove that they can solve problems that regular computers can't. If we're exponentially more sensitive to noise as we continue to grow the size of our quantum computer, then are we in a hopeless situation? Is this a dead end? And the answer is no. The answer is no, because we don't need to remain passive in the face of noise. We can actually come up with ideas that would actively protect our quantum system against noise. So quantum error correction, in fact, error correction in general, relies on using of redundancy. So, for example, if you're using radio communications, back in the day where people spoke on the radio, you're a pilot of an airplane, and your airplane code is ABC. You're not going to say the radio transmission channel ABC over, because A, B, and C would sound very similar to each other. And in the presence of noise over the radio communication channel, the control tower might not understand what letter you're referring to exactly. And that's why pilots would say Alpha, Bravo, Charlie, right? They're using long words, so that means there's redundancy in order to encode a smaller amount of information. And the reason they do that is because even in the presence of noise, differentiating Alpha from Charlie, it's much easier than differentiating A from B from Bravo from Charlie. It's much easier to differentiate from B to C. The same philosophy applies for digital communication channels. Let's say you want to transfer a single bit 0. It can be either a single bit, which can be either 0 or 1. If there's a little bit of noise, 0 will flip to 1, then you've lost your information. But if instead you transfer every 0 with 3 zeros and every 1 with 3 ones, then if a single bit flip, then it's okay. You can look at the majority ruling and recover the original words. Let's say I transferred 1, 1, 1. An error occurred and one of those flipped to 0 by forming a parity measurement or performing a majority rule, then I can recover the original word of 1, 1, 1. I use redundancy in order to protect myself against noise. In quantum mechanics, I follow similar philosophy. In quantum mechanics, the situation is a bit more subtle because I can't measure. Here, I've shown you a situation where I receive the information, I measure the information, I know what it is, and then based on the measurement, I can actually fix the error that occurred. In quantum mechanics, I can't bluntly measure, because if I'll bluntly measure, I'll erase the superposition of phase information in states. But the basic idea of quantum mechanics is the following. So I can have a quantum error correction code. This is the short code for quantum error correction, in which I use redundancy to protect my superposition. So instead of having a single bit, which is a superposition of 0 and 1, I create a superposition of 0, 0, 0, and 1, 1, 1. Now, clearly, this qubit does not exploit the full Hilbert space, the full set of possibilities that these qubits can be in. I don't have any amplitude in 101 or 001 and so on. This is a subspace of the full Hilbert space of possibilities of my quantum state. This is my error correction subspace. Now I build the error correction subspace such that if a single bit flipped, okay, an error occurred. So let's say the middle qubit flipped, 1, 1, 1, and 0, 0, 0 will be mapped onto 1, 0, 1, and 0, 1, 0. Okay? But the state of my qubit, the logical state of my qubit is unchanged. Okay? So if my error is bit flipped, what my error does is move me between different subspaces. But it doesn't corrupt my quantum information. Similarly, if the first qubit flipped, I'll be mapped from the subspace of 0, 0, 1, 1, 1 to the subspace of 1, 0, 0, and 0, 1, 1. But again, the state of my qubit is not corrupt. How do I correct my error? I need to perform a measurement, but the measurement I need to perform is not a measurement where I measure the state of all qubits. The measurement that I need to perform is a measurement that would only tell me in which of these subspaces I reside. For example, I can measure whether each of the pairs of qubits in my quantum computer are the same or in opposite states. So for example, here, both the first and the second qubit are in the same state, and the second and the third qubit are in the same state. And it doesn't matter where I am in this subspace, that's the case. Whereas in this case, these two are in the same state, but these two are in opposite state, and these two are in opposite state. And that's a clear indication on this subspace. So if I perform measurements that only tell me in which of the subspaces I am, and don't tell me anything about my superposition within the subspace, I can actually correct these errors. And by using such techniques, people have shown that we can actually construct quantum computers that are quantum computers that are fully resilient against the operation of noise. And that's the reason we also believe that we will be able eventually to build quantum computers that are beyond the noisy intermediate scale age that we are at now. So how are we doing with respect to time?
5 minutes.
Oh, okay. That's really much. So I actually went through about the first half of my talk, which was about an introduction of the concept of quantum computing. The second part is about how do we build quantum computers using laser-cooled trapped ions. Maybe I'll just cherry pick a few slides from here. But if anyone has questions on the first part, that's a good place for you guys to ask. Yes.
Can we have kind of more law for certain physics computer analog for quantum computers?
I'm sorry, maybe you can take down the mask just for the sake of asking the question.
Could we have kind of Moore's law analog quantum computing translated to quantum computing world?
Right. So Moore's law, for those of you who don't know, means that the number of transistors per area is going to double every 18 months. That was a prediction that was put forward by Gordon Moore in the 1960s, I believe, or 70s. And since then, the semiconductor industry actually followed that law rather accurately. By the way, it's not because Gordon Moore was such a prophet, it's because he actually set the working goal for the semiconductor industry for the decades to come. With quantum bits, there are, people have started thinking of scaling laws like this. It's not so much about the number of quantum bits per unit area, because that number is not really interesting, at least as of today. What people are interested in more is the number of qubits you can work with. It's the number of qubits. See, indeed, we see that the number of qubits that people can work with, the reason I'm saying can work with is because I can throw in 1,000 ions in my trap. That doesn't mean I have a quantum computer of 1,000 qubits. It's a workable quantum computer with a reasonable amount of noise, and there are precise ways of defining it. The number of working qubits would increase, would double itself every whatever unit of time, let's say a couple of years. And people have seen, we're just at the beginning. If you look at the largest quantum computers today, they have a few hundred quantum bits. and the effective number of quantum bits is 10 to 20, if you like. So we're really in the beginning of this trend, but the hope is, yes, that the number of accessible quantum bits would double itself every fixed period of time.
Thank you so much.
Okay, move on. Moving on. So as I said, we're using laser cooled trapped ions. They're cooled to microkelvin temperatures. They're trapped by electric fields. We use their internal degrees of freedom in order to encode information and choose such states. I'm not going to tell you which ions we work with. I'll just say that these ions are very similar to alkaline atoms that we use in laser cooling experiments. They have a single valence electron with a very strong dipole position that we use in order to laser cool and detect our ions. Some of these ions, these are fashionable choices, also have narrow optical transitions to metastable states, and these narrow optical transitions are very useful. I can show you two examples of how we encode a qubit in these trapped ions. We usually encode a qubit in the ground state of these ions. If these are ions with no nuclear spin, the ground state is single electrons, is two levels of the spin states of the electron. And the energy back between them depends on the magnetic field we apply on the system. In units of frequency, it's in the megahertz per Gauss range. So usually the transition frequency between the qubit states is in the megahertz range. In ions that have a nuclear spin, what you get is a hyperfine structure, and when you get a hyperfine structure, you can often find transitions that are first order insensitive to magnetic field noise. That means these are transitions between n equals 0 level and n equals 0 level. And these transitions are typically in the gigahertz range. The advantage of using these hyperfine qubits is that the phase relation between the two qubit states, because it does not depend on magnetic field noise is the dominant noise in our system, their coherence can be maintained for extremely long times. And here you see an example from Tsinghua University where the coherence, the phase relation between qubit states was maintained for 5,000 seconds, which is almost 2 hours. This coherence time, if you like, that's the quantum memory time of our computer. That's longer than any relevant time scale of our system. So trapped ion qubits are particularly coherent. Next thing we need to do is to be able to initialize and measure our qubit. So the way we initialize our qubit is by using optical pumping techniques. So as an example, with the narrow line with laser, we shove the electron from one of the ground states, spin states, to a metastable laser, and then optically pump it to P level. The electron can decay either to the down state or the up state. If it decays to the up state, that cycle repeats itself. If it decays to the down state, it remains there. So after this cycle happens several times, we actually reset our qubit to the downstream state, let's say the 0 state of our quantum bit. How do we detect our qubit? Again, we use the narrow line with laser. We shelve one of the spin state to the metastable optical level, and then we turn on the strong dipole transition in our qubit. We measure fluorescence. If you measure fluorescence, that's a good indication that the qubit is in the down state. If you don't measure fluorescence, it's a good indication that we're in the up state. Sorry, what you see here are the histograms of the number of photons we detect in a few hundred microseconds in case of being in 0 state, or in case of being in 1 state. You see that the histogram is very fat, around 20 photons. If you're in 0 state, or it's very small, this is a logarithmic scale. It's very small if you're in 1 state. So we can actually differentiate, we can measure our qubit and initialize our qubit with pretty high fidelity. The error in initialization or measurement, here we show data from our laboratory. That's measurement in the different bases, in the different directions in the block sphere. The error is on the order of 1 part per 1,000. This is data that comes from Oxford, where you can see the error goes all the way down to 1 part in 10,000. So the reset and readout in quantum computer, trapped ion-based quantum computers, is very high fidelity. I don't have much time, so I'll advance forward and show you ground state cooling and quantum measurement. What I'd like to show you is that, after having, I showed you before that we need, in order to have a universal quantum set of quantum gates, well, we need to be able to have is single qubit rotations and 2 qubit gates between each pair of quantum bits in the register. And what you see here on the left is the state of 1 out of 5 trapped ions that we have in our trap. So this is ion number 1, 2, 3, 4. And by focusing a laser beam, ion number 1, 2, 3, 4, this is if you like one, we're able to perform single qubit rotations of ion number 1, that affecting ion number 2, 3, 4, 5. We can do the same for ion number 2, 3, and so on and so forth. So we can actually take each and every qubit in our register and act on it. We can also take each pair of qubits in our quantum register and perform a control knot operation in them, or what we refer to as an entangling gate. So what you see here is the fidelity, so 1 minus the error of all the entanglement gates that are carried out on all pairs of ions in the register. You can see that in this case, the errors are in the 1% level. So that was the result of a 5-qubit quantum computer that we built. This is a universal quantum one-bit trapped ion quantum computer with 5 qubits. We're now in the process of working on our next generation 50-qubit quantum computer. If you remember the numbers before, in order to hit quantum advantage, what you actually need is 50 to 60 quantum bits, and this machine is likely to put us there. What you see here is a fluorescence image of about 50 trapped ions. I'm not going to tell you much about scaling up architecture. I'll just end by saying that in the 1940s, the first electronic computer in Israel was built at the Quantum Institute of Science. People started working on it in 1947, and its building was completed in 1954. Actually, this is something we take a lot of pride in, because in the early 1950s, there weren't many electronic quantum computers in the world. And Israel back then was a country with, food rationing. The economy was horrible. Yet people still had a vision of investing efforts and funds in building an electronic quantum computer. It was called the Weizmann, which is the Weizmann automatic computer. In order to pay tribute to this computer, we called our quantum computer the Weizmann quantum computer in 2022, and we hope that with enlarging this quantum computer, we will be able to achieve impact similar to what the original Weizmann had on the computing landscape, at least scientifically. So that's it. That's all I have to say. I mean, I had a lot more to say, but I see it due to time constraints. But I'll be happy to take questions.
Thanks for the very interesting talk. I think I like this closing slide, because this is something which refers to the question that I've been hearing about the importance, the impact of quantum computing. Because between this time and the Weizsäcker was built, or whatever kind of earlier electronic and the computer revolution that came like decades later, was a lot of tooling and so on. And I feel like we are back at this stage where we're basically programming gates and on this level. So what is needed to have actually the process of quantum computing as something that has an impact on general computing? What will be the time scale? What will be the tooling needed that the normal programmer will be able to work with those devices?
So it's a good question. I think that quantum computers, well, I'll start by saying that once quantum computers are sufficiently robust against the damaging effects of noise, and the number of qubits is sufficiently high. We're not talking crazy numbers. We're talking about 100 useful qubits, 200 useful qubits will already be able to make very significant impact in computation. I mean, one example is solving quantum antibody problems. These are problems that physicists are trying to solve in order to understand the behavior of materials. And they can't do it right now. Quantum computers will be able to solve that. So scientifically, that would already be significant advance. Similarly, if you look at problems that are not scientific but come from more commercial area, quantum computers of that size would have a tremendous effect. in regards to the tooling that we need to have there, is then a full stack quantum computer is not just the hardware processor level that I described. It has many layers to the stack above it. So a quantum computer like that, we need to have a compiler. Above the compiler, you would need to have, together with the compiler, you need to have a coherent control level. You need a concert of arbitrary waveform generators that know how to speak with each one of the qubits. You will need a quantum computing language that would translate the quantum logic that you're trying to execute into the machine language, into what the compiler can receive. So quantum computers do require multiple stacks. Quantum computers today are not at a stage where the stacks are modular and separable from each other. So unlike regular computers where different parts of the stack are independent, that you could work on a memory or on any other part of a classical computer, disregard almost completely the other parts of the computer. That is because the interface between the different pieces of the stack are already, there are protocols that standardize them. Quantum computers, that's not the case. Actually, every part of the stack needs to be intimately related to other parts of the stack. So today you see a lot of effort in creating exactly these tools that would turn quantum computers into useful machines that can have scientific and commercial impact. But it's in the making. These things are happening.
First, thank you for the very interesting talk. Unfortunately, there was no time to go in between the part, which is very interesting for us, because we were missing an ion system session. And I believe it's worth to make a few technical questions so we get the picture and you get the chance to say what you didn't get the chance to say. Right. Let us go to the process. You prepare a qubit perhaps in photonic qubit and then present it to the ion. Is that the case? Or you prepare instant?
So the ions are the qubits are the ions. So the qubits are atomic qubits. The way we create these atomic qubits is by resistively heating, usually resistively heating an oven that emits a thermal beam, whatever ions we're using. In this case, it's strontium ions. We direct this oven to the center of our ion trap, and then we photoionize these ions. And then what you see is these ions pop in. You see them. Here's a picture. You see them, appearing on the camera. The reason you see them on the camera is because we also have the laser cooling beam directly to the center of the trap. And you just look at the camera and you see them pop in one by one. Ding, 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 ding. Once you hit the number of qubits you're interested in, you shut down the oven, you shut down the photoionizing beam, and then you're left with these ion crystals. Now, because we work in ultra-high vacuum conditions, these ions can remain trapped for days. Okay, so once you trap them, they're simply there. And you can start working with them. So we don't work with photonic qubits at all. We use laser beams, laser light, in order to interface with the ion qubits that we trap. But the qubits are encoded by the ions.
And the coherence limitation is the vacuum itself, or there's some other factor?
No, there are. So I think coherence is, of course, if due to bad vacuum conditions, your ions would be kicked out of the trap, then that's a limit to your coherence. You have to keep in mind that ion qubits and the ion traps, if you work with laser cooled atoms, typically the depth of the potentials with which we trap atoms is very low. It's in the millikelvin scale. And that is because all the neutral atom trapping technology uses the atomic dipole moments as the way to apply forces on the atoms. Okay. You have to keep in mind that we trap ions not with their dipole moments, but rather with their charge, with a monopole moment. And the forces we can apply are orders of magnitude stronger than you can apply on neutral atoms. So the depth of our potentials is 10,000 Kelvin. So collisions with background atoms do not kick ions out of the trap. We will lose ions from the trap usually due to chemistry, due to the binding of some hydride. the turning of our strontium plus to strontium plus hydrides. All of a sudden, we'll see a smiling attitude. There are ions. That means one of our ions went dark. Then it's useless. So vacuum does not really impose coherence limitations. What mostly imposes coherence limitations is either magnetic field noise, as I've just shown you. Sometimes spontaneous photon scattering from the laser beams that we use in order to generate gates. We generate gates using laser beams. And then if during the operation of photons scattered, that means that there's a probability for the spin state of our ion to flip. That's another mechanism of decoherence. The fidelity of our gates can be also affected by the heating up, the increasing temperature of our ions in the trap. And our ions do heat up. They heat up due to electric field noise on the trap electrodes, which can be either due to negligent connection of power supplies to your trap electrodes. But even if you do the best job in the world, then there are also surface effects and eventually Johnson noise, which due to finite temperature generates electric field noise on the trap electrodes. So all these are decoherence mechanisms that we deal with.
So I guess that's why you use projecting technology. You have chips, right?
Yeah. So in fact, this 5-qubit quantum computer, the ions are trapped in a room temperature apparatus, and that's fine. The vacuum there is about 10 to the minus 11 torques, so we don't need that. When you go to 50 ions, you're much more sensitive to collisions with background atoms, and the reason for that is that unlike neutral atoms, because of the long-range Coulomb interaction between ions, if an atom from the background collides with one of the ions, it'll impart energy into the entire crystal. So we need to make sure that none of the ions in the crystal collides with background atoms. That's the reason we trap these ion traps inside the cryogenic trap. This trap is cooled to 5 degrees Kelvin, and at these temperatures, really nothing is in the form of gas. So the vacuum is much better. We can drive the system to pressures which are 10 to the minus 12, 10 to the minus 13 torque, and then suffer less collisions with background atoms.
Just one question. Do you use normal conductors or superconductors?
We use normal conductors.
Superconductor will not ahead of the amount.
So there have been some attempts on using superconductors. You have to keep in mind that in order to trap ions, you need to apply AC voltages, which have hundreds of volts in magnitude. Very often people have seen vortices and so on. What people have done and are still doing quite successfully is enclosing the entire trap within a superconducting box. And that's a very good magnetic field noise shield.
Okay, so only one question more. How much is the better in comparison with the with this about the microchips about this thing? Thank you.
It's a very good question. I should say that the process that we've seen in the last few years is actually amazing. A field that was, all of it was in academic labs pretty much, all of a sudden got the acceleration of the industry behind it. So I think there's a few things to say about it. One is that I'm not familiar with a single commercial or industrial effort to build a quantum computer which is not a spin-off of a particular academic group. And that is because the know-how that is necessary in order to build these machines does require the expertise of people who have spent 10, 20 years in the trenches. So I think that probably all, at least most of the industrial efforts are adjacent to academic labs. So in that sense, I'm not going to say that it's difficult to separate between them, but there's symbiosis between the academic effort and the industry effort. Secondly, I think it's very difficult for academic labs to compete with the resources, the engineering resources that the industry can bring to the table. So if you look at the processors that are built at, with startup companies and the giant tech companies, they're larger and they're pushing with a much stronger engineering force. So currently the largest quantum computers are actually in the industry, not in academic labs. And the last thing I'd like to say about it is that, quantum computers in the vacuum tube age of quantum computing. We haven't invented the transistor. So I think it's not all about engineering power and resources. There's still a lot of weight and significance, creativity, and coming up with ideas that are completely new and do not follow the beaten track. And that's where I believe the academia has a role, because academic research should not be directed necessarily towards building the largest quantum computers, because it can't compete with the Google idea. Academic research should be directed towards coming up with a transistor of quantum computing, coming up with new paradigms, coming up with new ideas that the industry can then take and industrialize.
So thank you very much, Professor Ozeri, for this nice talk. I'm so sorry for doing this more time for the question, but I hope that in the future we will have you again to have another talk with our academic and all of our students. So now, thank you, Professor Ozeri, for the So we have this for you. Vamos a comenzar con una pequeña visita a nuestros laboratorios. Nos disculpamos por